My name is Vinay Kamidi. I recently graduated from Virginia Tech with my PhD, and I'm currently working as a senior software and controls engineer at Aptronic. I'm delighted to be presenting to you all today my paper titled Distributed Quadratic Programming Based Nonlinear Controllers for Periodic Gates on Legged Robots. I'll begin this talk by providing a brief motivation. In the recent years, quadratic programming based controllers have received extensive consideration for the real-time planning and control of legged robots. For example, they have been used in the context of model predictive control for path planning of reduced order locomotion models and whole body motion control of full order models. The bedrock of these approaches considers the centrality structure. Despite the superior performance of centralized QP-based controllers, they exhibit a lack of scalability with the increasing complexity of modern legged robots, wherein each new robot has more degrees of freedom than its predecessor. Turns out, nature employs alternative approaches towards locomotion control. For example, in a 1994 study on a domestic cat, investigators surgically severed the spinal cord of a cat, removing the connection between the brain and the hind legs. In the low-quality video on the left, the cat was placed on a treadmill, wherein despite the lack of connection, the cat was able to execute a wide variety of gaits. This indicates that some form of locality exists in nature. In the control society, one form of locality is abstracted as distributed control and has long been a topic of interest in the context of large-scale systems, control of swarm robots, etc. Distributed QP-based approaches have also been developed, but in the context of large-scale systems wherein the problems are sparse in nature. They have also been in use in the swarm robotics community, but the existing methods translate at best to weakly coupled systems. On the contrary, legged robots are underactuated and nonlinear in nature. Synthesis of distributed controllers for a single-legged robot results in a strongly coupled system that present non-sparse structures. This motivates the development of distributed QPs for high degree of freedom legged robots with strong coupling amongst their subsystems. In the context of legged locomotion, two prior works exist. In the first work, minimal communication of states was assumed between the two subsystems, but no such assumption was made between the individual QPs. And furthermore, the method was only validated in simulation. In the second work, while a control Lyapunov function-based distributed quadratic program formulation was presented, it was condensed to a model-free QP in order to be able to implement on hardware. Contrary to these contributions, in this work we present a network of distributed QPs with an inherent feedback structure that preserves the steady-state solution of the centralized QP on periodic orbits. Additionally, we present a set of sufficient conditions under which the solution of the local QP asymptotically converges to the steady-state solution. Finally, this work also takes the effort to demonstrate the practicality of the approach on an 18 degree of freedom quadrupedal robot A1 by condensing the general formulation to a network of two distributed QPs. This, to the best of our knowledge, will also be the first model-based distributed control implementation on a legged robot. Formally, we are interested in synthesizing distributed QP-based nonlinear controllers for periodic orbits of hybrid models of locomotion. More particularly, we propose a network of local QPs decomposed from a centralized QP. We provide a channel of communication between each local QP with the goal of achieving no performance degradation. The general notion of centralized QP is provided on screen, which is written down as a composition of M subsystems with a quadratic cost function and some equality constraints that dictate the dynamics of the system, and some inequality constraints that enforce torque and ground reaction feasibility conditions. From here on, I will continue the analysis in discrete time as the local QPs will be solved digitally. Once we start decomposing the equality constraints, or for that matter of fact the dynamics of the system, we start to notice the inherent coupling between each subsystems. This strong coupling means that subsystem I is dependent on subsystem J's terms, which it does not have access to. In order to address this limitation, I make the assumption that each local QP has access to the optimal solution of the other local QP. However, since it is not possible to have the solution of the other QP at the same time step, let's say time step k, I provide the solution of the other QP at time step k-1. This is captured in assumption 1. In addition to this, we are also interested in guiding the local QPs towards the steady-state solution. For that purpose, we make the assumption that each local QP has access to the steady-state solution, which is captured in assumption 2. A more concrete shape can now be given to the problem of synthesizing distributed controllers. More particularly, we seek to design M-local QPs whose optimal solution asymptotically converges to the steady-state solution of the centralized controller. To achieve this, I introduce additional terms to the general QP. The reformulated local QP shown on the screen has two new terms in the cost function and the equality constraints that are eta and zeta respectively. These terms contain some feed-forward terms, alpha star, which are the Lagrange multipliers corresponding to the equality constraints of the ith QP available by virtue of assumption 1, and u star, that is the steady-state solution available by virtue of assumption 2. Additionally, it also has feedback terms that penalize the deviation from the orbit or the steady-state solution. It introduces gain matrices Lij and Kij. A formal tool will be introduced shortly to tune these parameters. For now, I encode the tunable parameters in the vector theta. Before I provide a tool for the proper selection of the parameter vector theta, I want to establish that the steady-state solution available to me is the unique optimal solution of the proposed local QP. This is presented by theorem 1, whose proof is pretty straightforward. We start by assuming that at time step k-1, solutions for local QPs coincide with the corresponding steady-state solution. This will reduce the terms eta and zeta to just feed-forward terms. Then by making use of assumption 2, that is the existence of a periodic solution and the fact that the inequality constraints are inactive, the Lagrangian for the local QPs are just in terms of the equality constraints. Further, if you take the first derivative of the Lagrangian, you can see that the resulting term coincides with that of the first derivative of the Lagrangian from the centralized QP. This indicates that ui is equals to ui star is indeed the unique optimal solution. From theorem 1, it was established that local QPs preserve the steady-state solution. We next can study the properties and convergence behavior for the solutions of the proposed local QPs. For that, let us assume that the system state evolves on the periodic orbit. Then according to the feedback structure, optimal solutions at time k+1 depends on the ones from time k. This is more precisely noted in the flow map as shown on the screen. At this juncture, we also make the assumption that the equality constraint matrices of the local QP, AII, are full row rank on the periodic orbit. This is encapsulated in assumption 3. Now we are in a position to present the following result that will enable us with the proper tool to choose the parameters of the vector theta. The proof for this theorem is immediate. From theorem 1, we know that ui star is the unique optimal solution for the local QPs. We also know the cost and constraints are smooth, i.e. C infinity. Now since the inequality constraints are inactive at ui equal to ui star, the active constraints are reduced to the only ones enabled by the equality constraints. Then from assumption 3, the gradients of the equality constraints with respect to the decision variables are full rank. Hence, sufficient conditions of Fiako's theorem are satisfied. This guarantees the existence and uniqueness and C1 continuity of the solutions with respect to the terms eta I and zeta I on an open neighborhood of u equal to u star. The fact that eta I and zeta I are smooth in terms of u completes the proof of part 1. Part 2 is the immediate result of the flow case stability theory for periodic and discrete time systems. Now the practical takeaway from this is part 2 of the presented theorem that states that the periodic solution is locally asymptotically stable if the eigenvalues of the monodromy matrix lie inside the unit circle. The monodromy matrix is the product of the Jacobian of the flow map that was presented earlier. This allows us to validate if the parameter of the vector theta allows asymptotic convergence to the steady-state solution. As a representative example, we consider the problem of quadrupedal locomotion. More particularly, we consider that a quadruped is composed of two bipeds separated at the geometric center. Namely, we call them the front and the hind subsystem. The network of distributed QPs is then condensed into a two-distributed QP network. The condensed form of the general local QP for subsystem 1 is presented on the screen, wherein gains L11, L12, K11 and K12 are tunable parameters. First, a centralized QP was formulated with 36 decision variables, which were torques, ground reaction forces and slack variables. Additionally, the centralized formulation had 24 equality constraints and 70 inequality constraints. In the distributed formulation, this reduced to a total of 18 decision variables 12 equality constraints, and 35 inequality constraints per QP. This reduction resulted in a reduced solve time from 0.13 milliseconds in the centralized framework to 0.034 milliseconds in the distributed framework, using an existing solver named QP Swift. The key takeaway is that the network of distributed QPs allows us to represent a high-dimensional problem as a composition of multiple low-dimensional problems. In this work, we are interested in the QP-based input-output linearizing controllers. In order to facilitate that, we consider a set of holonomic output functions, referred to as virtual constraints, to be regulated for the whole body motion control. For the problem of trot gate, in a traditional centralized control framework, a total of 12 virtual constraints would suffice. This is indicated on the figure to the left. The 12 virtual constraints here would involve the position and orientation of the body frame and the Cartesian position of the two swing legs. However, this would not result in a uniquely separable virtual constraints for the two distinct subsystems when decomposed. In order to accommodate that, we choose an 18-dimensional output function for the centralized framework and call this the augmented formulation. More specifically, 6 outputs are designated for the Cartesian coordinates of the center of masses for the front and hind subsystem, and the remaining 6 outputs are redundant and reserved for the absolute orientations of the center of masses. The last 6 outputs are reserved to control the Cartesian position of the two swing leg ends. To address the redundancy in orientation and to ensure the validity of full rank assumption, we introduce slack variables to the QP formulation. This ensures 9 virtual constraints are available for each subsystem, as shown in the figure to the right. In order to validate the synthesized distributed controller, we perform an extensive set of experiments. First in a simulation environment, then in indoor lab settings, and followed by various outdoor environments. A centralized QP for the problem of in-place trot in a quadrupedal robot was first solved and a steady-state orbit was consequently extracted. Note that this was the only time a centralized QP was solved in this work, and we make use of the same steady-state orbit throughout all simulations and experiments. Here we show selected few results from simulations. In particular, we would like to highlight that the performance of the distributed controller is preserved even in the presence of mass uncertainty, simulated by a 4 kg object fixed on top of the robot. Similarly, no change in performance was observed on introducing terrain uncertainty by lacing the simulation environment with blocks. Next, we wanted to differentiate the distributed controller from the centralized control scheme. To extract meaningful dissimilarities, we introduced additive white Gaussian noise with a 1 decibel signal to noise ratio into the velocity measurements corresponding to the components of the front right leg. Both centralized and distributed control schemes were simulated in this configuration, as shown to the left. On the bottom right corner, torques corresponding to the hip roll of the right hind leg is shown. It is visibly notable that noise injected in the front subsystem significantly propagates into the hind subsystem in the centralized control scheme. We further quantify the propagated noise in the hind subsystem and report that a 18.35 decibel SNR in the torques of the hind subsystem was recorded in the centralized control scheme, as opposed to a 37.37 decibel SNR in the distributed control scheme. Note that lower SNR indicates higher noise in the signal. This demonstrates that the distributed control scheme presents better noise rejection properties. To illustrate the practicality of these synthesized distributed controllers, we perform rigorous blind locomotion experiments in indoor lab settings. An external PC was made use of to run the controller at 1 kHz. The block diagram illustrates the various other components not in scope of this discussion but were made use of to run successful experiments. In the first experiment with the distributed control scheme, a trot gait and a forward speed of 0.7 meters per second is prescribed. The plot in the bottom right corner of the screen shows that the torques in the distributed control scheme converge to the steady-state torques. You can see that the steady-state torques are smooth, as I still use the same orbit that was originally extracted in simulation. A curated list of other experiments with the distributed controller on A1 quadrupedal robot that were aimed to demonstrate the inherent robustness is shown here. Various gates and uncertainties were introduced to evaluate the performance of the controller. More particularly, we show backward trot in the presence of terrain uncertainty, lateral trot in the presence of terrain uncertainty, forward trot in the presence of terrain uncertainty. Further, compliant surface and payload uncertainty experiments are also shown here. In order to further emphasize the inherent robustness of the distributed controller, two other experiments were conducted wherein aggressive disturbances were delivered to the A1 quadruped while locomoting in place. In the inset of each video, a plot is provided that illustrates the nominal limit cycle, i.e. the one corresponding to the centralized controller obtained in simulation, and another limit cycle that corresponds to the respective experiments. It can be seen that in both these plots, the limit cycles significantly deviate from the nominal limit cycle when the disturbance is injected into the quadruped. However, the distributed controller successfully manages to stabilize the system despite of the harsh and unexpected impulses and pulls back the limit cycle close to the nominal limit cycle. Lastly, I want to end with some videos of the distributed control algorithm being used outside the lab in natural environments to further show robustness. Here, we show the performance of the algorithm on loose gravel, mulch, and demonstrate the transition from and to different terrains and locomotion at the commanded speed of 1 meters per second. Thanks for listening, and I'll open up for any questions now.